Right, so just again to reorient you, we had yesterday's lecture on malaria, today's on TB and leprosy, then we'll be looking at emerging infections, eradication of disease and lab diagnosis later in the course. And has anyone not found the Bio303 module on Facebook? Right, so what is tuberculosis? It's usually an infection of the lungs, although actually it can spread to many different organ systems in exceptional cases, but it's usually of the lungs, and it's caused by Mycobacterium tuberculosis. There's a lot of unusual things about this infection. Most of the infections are asymptomatic, or what we call latent. The organism's just hiding there, not causing clinical signs and symptoms, not even really causing tissue damage in most patients. But about 10% of the time it leads to active disease, and we have this so-called quartet of fever, malaise, night sweats and weight loss, the quartet of TB, and usually a cough, and using a bit of jargon there, the word hemoptysis means coughing up blood. So you may cough up blood as part of the cough. In 2007, figures were around 13.7 million chronic active cases, 9.3 new cases, and nearly 2 million deaths. And around 500,000 cases of multi-drug resistant TB. But we're starting to get ahead of ourselves a bit there, so let's pull back a bit. When we look at the history of this disease, I haven't put much in about the history of the disease. It is actually an ancient disease, and we can see the hallmarks of tuberculosis in ancient bones. People can actually detect some of the lipids produced by TB in ancient bones, and people have been able to actually amplify DNA from very old specimens. And there's a couple of papers there I've linked here, put here. There are links to these actually on the Facebook site. Another interesting feature of TB is that it initially was thought, until recently, that all of the cases of TB, all of the instances of the bacterium around the world, were all very closely related to each other. And sometimes it's described as a monomorphic organism because it really not very changeable, until they actually started looking at some isolates from Africa, from East Africa, and this guy Roland Brosch and his colleagues did this, and they realised that actually most of what we see around the world is just a small part of the variation within Mycobacterium tuberculosis, and what they posited was that they'd found the progenitor, which they called Mycobacterium prototuberculosis, and they'd found much more variation in the progenitor than was in what we normally recognise as M. tuberculosis. And they speculated that actually there was an ancient history of the progenitor alongside humans in Africa before the emergence of humans from Africa. In terms of tuberculosis in history, it's had a devastating effect on society. If we went back 100 years ago, about 1 in 5 of the population was destined to die from tuberculosis. And the list of famous people that have died from tuberculosis is actually quite long. Chopin, Keats, the Brontes, Kafka, D.H. Lawrence, George Orwell, as you can see there. This is Keats. And John Bunyan, in one of his poems, wrote, well, one of his essays, I should say, about the life and death of Mr. Badman, a kind of moral tale. He identified tuberculosis, or consumption as it was known then, as captain of all these men of death, as the most important cause of death. Just to give you a feel for this, again, if we look at these two individuals here, Muhammad Ali Jinnah, the founder of Pakistan, and Nelson Mandela, who was the first president of post-apartheid South Africa. Now, Jinnah in the 1940s fell ill with tuberculosis, and he died at the age of 71 in September 1948, just around a year after Pakistan had gained independence. So he really hadn't got a chance to lead the new nation for very long and lead it to a satisfactory, stable situation. Just by a sad quirk of history, he just missed out because the first randomised trial of an agent that worked against tuberculosis, streptomycin, occurred in 1947, happened here in the UK, carried out by the Medical Research Council. So if Jinnah had just survived a few more years, he probably would have got treatment. Compare this with Mandela, who got tuberculosis around the same kind of age, at the age of 70, in 1988. He was treated successfully and then went on to leave prison and lead South Africa to this new multiracial democracy, first post-apartheid president, retired from office, which actually is a notable thing, because in many new countries you get a situation where someone starts off looking like a nice benign individual but ends up hanging on to power. But he set the precedent there of actually retiring from office, and he's now still alive at the age of 92. It's interesting to speculate what would have happened if Jinnah had survived. Maybe Pakistan, I mean, it had a stormy course in its first few years, and really since then, with military dictatorships and so forth. Interesting to speculate. Mycobacterium tuberculosis is rather different from almost every other bacterium. So you've probably learnt about E. coli and Staph aureus and so on, and think you know about bacteria. This one is quite different. It has a very complex lipid-rich cell wall, probably the most complex cell wall in nature, actually. The gram stain doesn't work with TB because it can't even get in, let alone be leached out again. And so if we want to see these organisms, we have to use a different kind of approach known as acid-fast staining. And so these organisms are called acid-fast bacilli in the jargon, or AFBs. It grows very, very slowly. So it takes at least a couple of weeks, 3 weeks or so, before it will grow in the laboratory. And in some cases, it can take as long as 3 months for M. tuberculosis to be recovered from a clinical specimen. It's also particularly special because it's a hazard to lab and hospital staff. So we recognise the risk of catching tuberculosis from the sample is quite appreciable. And so these samples are actually handled very specially. They're double bagged in a container, they're labelled up properly, and so everyone looks after them, treats them with great respect. Mycobacterium tuberculosis is also different from most other bacteria because it's resistant to all the common antibiotics that you might come across, you know, amoxicillin and penicillin and things like that. It actually, to treat tuberculosis, requires months of multi-drug treatment with special agents. And almost all the agents we use to treat tuberculosis, certainly the frontline ones, are actually dedicated to treating tuberculosis alone and are not used in any other context. Another interesting feature is that this is an intracellular pathogen. So it actually thrives inside macrophages. So the macrophage is there as the kind of frontline troop, one of the frontline troops against infection. But this organism has managed to colonise that environment and live inside it. And it forms these things called granulomas, special kind of lesions, which I'll say more about in a moment. Antibodies have no effect on tuberculosis because it's living inside cells, and to get protection you need a cell-mediated immune response. So what does the natural history of tuberculosis look like? Well, the so-called primary infection, when you first come across the organism, you breathed it in usually, this gives you these non-specific symptoms, which I mentioned, or in many cases it's completely asymptomatic. You don't know you've been infected. As I say, the commonest route of infection is through the lung. You breathe it in, but it is possible to get infected in other ways. So if you ingest the tubercle bacilli, and this used to happen in days gone by before we pasteurised milk, one particular form of the tubercle bacillus, the bovine tubercle bacillus, could be found in milk, and this would then find its way into the tonsils and cervical nodes, or it would actually infect the small bowel and then go to the local mesenteric lymph nodes. It is also possible to get tuberculosis from direct implantation of the organism into the skin. So Lennox, who invented the stethoscope, he died this way because he was doing an autopsy on a patient with tuberculosis and managed to get some implanted in his hand, and then it spread from there to cause widespread disease. So what happens next? Well, in a few cases, not many, you get what we call progressive primary infection. You can get local erosion, dissemination. You can get metastatic infections, we call it, where the organism spreads throughout the body. So TB meningitis can result, where the organism gets seeded into the meninges and then causes a kind of indolent, but slowly progressive infection, which is, if untreated, usually fatal. Most of the time, though, after that, or even there isn't any progressive infection, it just goes latent, and it may stay latent for decades. So someone might get infected as a child and only reactivate their TB in late adult life. And reactivation can come about from various reasons. Sometimes it just happens for no obvious reason. If a person becomes immunocompromised, so they get cytotoxic drugs for cancer, or they have a transplant and they become immunosuppressed, then that can lead to reactivation. As we'll see later, if they get infected with HIV, that can cause reactivation. And even just things like diabetes can actually play a role. So this just puts that picture there into a figure. So you've got latency, primary progression, non-infectious or infectious, or reactivation. All of these as options there. So what does tuberculosis look like in more detail in terms of clinical features? Well, I've already mentioned this quartet of so-called quartet of tuberculosis: fever, malaise. Malaise is a technical term used by medics, just means feeling unwell, just feeling horrible. Weight loss, and then night sweat, so sweating profusely at night, soaking the sheets every night time. And then these focal features, particularly if this is of pulmonary tuberculosis. Radiological features, what we see on an X-ray, we usually see these opacities in the upper zone, and there are a number of features that we see. We see cavitation. So if you look on this X-ray here, you can see this here is a cavity. Another thing that we'll see in long-standing tuberculosis is that around the cavity you get the formation of calcification. You get radio-opaque material laid down. And finally, the other key feature is what we call hilar shadowing, which this is the hilum, this area that surrounds the heart. And these lymph nodes around the heart actually swell up and give rise to this hilar shadowing. There is a form of TB called miliary TB, where you get this widespread dissemination and it spreads all through the lungs, and there you see this very diffuse kind of nodular shadowing in the lungs. I mentioned already the idea that this disease causes granulomas or granulomata, and what happens is that you get this recruitment of macrophages with the Mycobacterium in them. They then sort of act as a nucleation point. They attract lymphocytes. Some of the macrophages change their phenotype, become so-called foamy macrophages. You get things like called giant cells, and you get death of cells in the central cavity, or the central part of the granuloma, and you get a process known as caseation. It's a strange fact of life, but pathologists often name pathological processes after food. Does anyone know what caseation means? It means forming cheese. So it's this kind of cheesy material that forms in the middle of the granuloma. It's a strange thing to think about when you're looking down the microscope, but that's how they named it. It's casing or caseation. And these granulomas can grow. They can then break open, particularly if they're, say, in the lining of an airway. If the granuloma ruptures, then it releases additional mycobacteria freely into the environment, and people can cough them up, and that's when they become infectious. So, enough about pathology. How about control? How are we going to actually control tuberculosis? Well, the main way in which we've eliminated it in our own society here in the UK is through general improvements in hygiene, housing, diet. You know, we don't have such overcrowding as we had before. People eat well. We can control animal reservoirs and the transmission from animals. So, as I mentioned, there is tuberculosis in cattle, bovine tuberculosis, and this can spread to humans, but that is extremely rare now because of pasteurization. There are a lot of efforts in this country also to control the animal reservoir, to get rid of bovine tuberculosis at source in the cow herds. And some of you probably come across in the news this business of trying to cull badgers, because badgers are thought to be a vehicle that transmits infection between one cow herd and the next, and acts as a reservoir in the environment. It's all very controversial, in fact, because the evidence is rather equivocal as to whether, well, I think badgers do carry tuberculosis, but whether actually culling them will make a difference is a matter of great controversy. An interesting fact, though, before people sequenced the genome of tuberculosis, and there was a bovine form of tuberculosis, but we all assumed that humans caught tuberculosis when they started herding cattle, and this was a disease that we got from agriculture and domestication and so forth. In fact, it turns out it's the other way around. The bovine form of tuberculosis is the derived form of the human form, and the cattle caught it off us at the start. Vaccination is another form of control. You can immunise with BCG, and that's traditionally been done in the UK at the age of 11 to 13 years. And in certain areas, it was done, in certain at-risk areas, it was done to infants or at birth. Also important is case management and follow-up. So infection control. We'll put these patients into side room isolation if they're in hospital, if they're so-called smear positive. So those are cases where we can see the bacterium down the microscope. There's a kind of rule of thumb that if you can actually see the bacterium when you stain up some sputum, so-called smear positive, that means the patient's infectious. If you can grow them but you can't see them, we generally say that's smear negative tuberculosis and they're unlikely to be infectious. Diagnosis relies on, as we mentioned before, microscopy. You culture the organisms and you do sensitivities. And then you have treatment. Treatment, when applied properly, rapidly renders cases non-infectious. So finding infectious cases and treating them is one of the linchpins of tuberculosis control. The other thing we do is follow up on contacts. This is what we call a notifiable disease. So if someone is diagnosed as having tuberculosis, the doctor in charge, whoever made the diagnosis, has to then notify the local public health authorities, and they will send round someone to go and investigate the person's circumstances and look at their family members and so forth. Now let's just say a few words about BCG. BCG stands for Bacille Calmette-Guérin. It's a strain that it's a live attenuated vaccine. It's a vaccine strain that was derived from a virulent isolate of the bovine tubercle bacillus. And in a remarkable effort, these guys actually managed to attenuate the bovine bacillus by subculturing it repeatedly in the laboratory. And they did this not just for a few weeks or months, but for years, between 1908 and 1921. Over 230 serial passages were done. And by the time they got to 1921, the strain had become safe in animals, didn't cause disease anymore, but was able to vaccinate them, provide protection against challenge with virulent M. tuberculosis. So one of the most remarkable things is that this has been given now to over 3 billion people. But the trials that have been done using modern trial approaches, proper epidemiology, proper power, getting the right power and all those kind of things, these show variable efficacy. So in some populations, for example, here in the UK, one of the first trials showed 80% protection. But in other studies, for example, a study in Chingleput in India showed 0 protection. And so there's a great deal of, it's really unclear what's going on. There are various possible explanations. One is that, in fact, people in Chingleput come across environmental mycobacteria so often that they effectively are already vaccinated as much as they can be against TB, and BCG can't add anything, whereas in this country we don't come into contact with those environmental mycobacteria and BCG still has a role. There is also this problem that if you have HIV or any other kind of cellular immune deficiency and you get given BCG, there is a risk that you will get disseminated infection with the vaccine. So although it's attenuated in normal people, in those individuals it can still cause a condition known as BCGosis. Coming back to diagnosis, just to look in more detail at that, I mentioned microscopy and culture. Stains poorly with the gram stain. We rely on acid-fast staining, and there are 2 conventional methods that are used here. One is known as Ziehl-Neelsen staining, and what this does is leaves you with this kind of picture here, where you have this bluish background and these purple bacilli that you can see often in clumps. This is, say, of a sputum sample. The problem is that actually looking for one of those little purple blobs in a sputum sample might be a very time-consuming business, having to search for many, many fields and being quite clear what you're seeing. So as a quicker screening test, people often use this auramine fluorescence staining, where you actually stain the bacterium with a fluorescent stain, and then you can scan through many, many fields very quickly, and you can see the one bacillus lighting up against the darkness very quickly. It's slightly less specific than the Ziehl-Neelsen, but perhaps more sensitive. The other thing we do is culture, and again, this is kind of every level. This is a kind of special organism. We do things strangely when we come to TB. So instead of growing it on agar plates that you might be familiar with, this one we actually grow on a slope here inside a screw-top container. And the reason for that is twofold. One is, if we just put them on agar plates, because they take weeks to grow, the agar plates would just dry out. And if you leave agar plates for long enough, they turn into things that look a bit like prawn crackers that you get with the Chinese takeaway. They just shrink down and they're useless for growing anything. What this is effectively a kind of omelette. You actually dry down this medium containing egg white, I should say, and it forms this solid medium which retains its moisture and provides a platform for the bacteria to grow on even after weeks or months. The other thing is, of course, if you have a screw top there, you stop the moisture escaping, but also importantly, because this is a very dangerous pathogen, you stop the organism from escaping, so that the handler doesn't actually get contaminated with the organism. Anyway, once it's been growing for a few weeks, it gives rise to these colonies here, which have been described on the Lowndes and Jensen slopes as being rough, buff, and tough in their appearance. They look a bit like breadcrumbs that have been scattered over there. There are problems with diagnosis, with using these kind of conventional microbiological approaches. One is that we actually only find out about tuberculosis when someone turns up with symptoms and they cough into a pot for us. So this is called passive ascertainment. We don't go out there and screen large numbers of people. And often someone will come to the clinic, they'll have a sample taken, And if they're not smear positive, or if they are smear positive but there's a bit of a delay, they may go home again, and there may be quite a considerable delay before they get treatment, and they may be coughing tuberculosis around for days or weeks afterwards. An alternative approach to making a diagnosis of tuberculosis or detecting infection is to actually engage in what we call tuberculin testing. So here what you do is you take something called PPD, purified protein derivative, a kind of pickled version of the bacterium, and you inject this into someone's arm. And what you're looking for here, you look for a reaction within 48 hours, at 48 hours, and you're looking not for erythema, so you can see there's a bit of reddening over this here. That's not what we want to measure. What we actually have to look for is induration, so it actually goes hard, lumpy. And you can run your finger over it and you can feel that kind of lump there under the skin. And what this shows us is that the patient has had infection with M. tuberculosis. It doesn't mean that they are actively, the disease is active and that there's any problem. It just means they've been exposed to the bacterium. In our population here in the UK, it also is very commonly positive because people have had BCG vaccination. So this test doesn't distinguish between exposure to BCG, having been vaccinated, and exposure to virulent tuberculosis. In populations where they don't use BCG, and in the US they traditionally didn't use BCG, it actually does provide a useful test if someone's been exposed, and you can say, oh, well, they've been exposed and therefore they're at risk of developing tuberculosis, and you can give them some treatment, a cut-down version of the normal treatment you give for TB, effectively kind of prophylaxis that will prevent them from ever getting clinical infection. But we can't do that in the UK because we all had BCG. If it's negative, it means that they haven't been infected or vaccinated, or that they're so profoundly immunocompromised that they can't mount a response, but usually it's not the case. Now again, just to ram home, TB is such a difficult organism, a difficult condition. When we treat, we have to treat with multi-drug regimens. The reason we do this is twofold. One is if you just give a single agent, you will get resistance occurring in about 50% of the cases. The patient will relapse a few months later, come back. So you treat them with streptomycin alone. They will come back and they will now have a streptomycin-resistant population of bacteria, because 1 in a billion or whatever it is of the bacteria will be streptomycin-resistant at the outset. You kill almost all the other organisms apart from that one, but that one then grows up over time and forms a new population that's fully resistant. It's a process of Darwinian natural selection going on. So if we give 2 drugs, if we give 3 drugs, or if we give 4 drugs, then we can prevent that resistance from happening. It also, when these drugs act together, they act what we call synergistically. They achieve a more rapid kill and a more rapid eradication of the bacterium and a more rapid return to normal health as well. So they're actually more effective in the short term as well. So what we do is we have an initial phase of 3 drugs for 2 months and then a continuation phase of 2 drugs for 4 months. So 6 months in total. And these different regimens that the WHO recommends there. So you can have isoniazid, rifampicin, ethambutol and pyrazinamide as your normal starting regimen, and then 4 months of isoniazid and rifampicin, or you can have streptomycin instead of your pyrazinamide. Now you might think that this is a dreadful regime, 6 months, and it is. It's a long time to treat someone. But if you ask any kind of elderly physicians, they'll say this is almost a miracle. Because in living memory, tuberculosis was untreatable. Back in the time of Jinnah, it was like getting lung cancer is now. You've got tuberculosis, that's it, you prepare your will and you're going to die. You might not die quickly, but you will die. Or when the first regimens came in, they were for 18 months or a year. And then they came down to 9 months, and now we're down to 6 months, and we have solid evidence that 6 months in uncomplicated cases is good enough. So there has been considerable progress in this area. Another key change in recent years has been the adoption through the WHO of what's called DOTS, Directly Observed Short Course Therapy. And what this means is you actually get the individual who has tuberculosis to take their drugs while being observed by someone else. Now, if you can imagine, I don't know how many of you have taken any tablets for any period of time, but actually remembering to take tablets, even for a week or two, can be challenging. When you've got 6 months of it, it's hard to just remember to keep doing it. Patients also, they quickly get well in the sense of feeling well, but if they stop treatment after a month or two, then they will almost always relapse. And so it's very important that you have to keep the treatment going. So this is where you're getting someone other than the patient to come and observe them. It requires these components here, various components. The local government has to buy into it. You get case detection by sputum sphere microscopy, as we mentioned, the acid fast staining and so forth. Standardized treatment regimen, directly observed for at least the first 2 months. So those are the 2 months where you sterilize the patient of the tuberculosis and stop them being infectious. You have a regular drug supply, and you have a recording and reporting system that looks at the treatment results and checks that someone doesn't actually relapse. As I say, there are problems. I mean, even with this kind of regimen, people fall out. They don't want to keep taking them. There are problems about ethics as well. I mean, the idea that, you know, someone grabs you by the scruff of the neck and says, "I'm going to watch you take your tablets," is a bit patronising. And some people have said, you know, this is not the way we should be treating patients. We'd be respecting their autonomy and all that kind of stuff. But anyway, it does work. It's been implemented in 184 countries. There's actually, for multi-drug resistant TB, there's a variation called DOTS Plus, which also appears to be very effective. So moving more on towards TB eradication or control, how do we stop TB? Well, the Stop TB strategy came about a few years ago with a vision of a TB-free world. And the idea was that we want to substantially reduce the global burden of TB by 2015. And you can see here the objectives listed: universal access to diagnosis, patient-centered treatment, reduce the burden, protect vulnerable populations, new methods, and promote human rights. And one of the Millennium Development Goals, Goal 6, Target 8, to use the kind of bureaucratic way in which these things are described, was to halt and begin the reverse of the incidence of tuberculosis by 2015. And these targets were linked to the Millennium Development Goals, endorsed by the Stop TB Partnership. And so the aims there are to reduce the prevalence and deaths by tuberculosis by 50% relative to 1990 by 2015. And by 2050, eliminate TB as a public health problem. So those are ambitious goals. So the global plan to stop TB was launched at the World Economic Forum in Davos in Switzerland in 2006. And again, one of our heroes in this area, Bill Gates, got involved in this, pledged $600 million. There's now $56 billion being spent between 2006 and 2015 to treat 50 million TB patients and save 14 million lives. With the aims of providing improved access, new drugs, new vaccines, new diagnostics. So it's actually, you know, it's quite enlivening when you recognise that these global efforts are going on and that people are actually thinking about the whole planet and the global village rather than petty local problems. There are problems. It's not going to be straightforward. And this is from a review. I've actually put a link. There's a special issue of Science magazine last year. I'll put a link up on the Facebook site. You can have a look at that. But here are some of the things from that review listed to say what problems there are. You know, problems in inconsistent infrastructure, difficulties in diagnosis and disease biomarkers, failure of BCG, failure of chemotherapy to secure patients, failure of drug discovery programs. In fact, let's just boil it down to 4 obstacles to progress and spend a few minutes talking about those. we've got the HIV associated TB epidemic, drug-resistant TB. We need better diagnostic assays, and we need something better than BCG. So one of the big problems is HIV and TB work together in this horrible synergy. 15% of TB cases globally are HIV positive, and TB accounts for nearly a quarter of all deaths from HIV/AIDS. Most of these cases that have HIV and tuberculosis are found in Africa, and one country in particular carries a horrible, terrible burden. That's South Africa, with 25% of the global burden of TB and HIV positive individuals. But you can see these figures are not good anywhere in the world. There's no grounds for complacency. But one thing that does seem to work is if you give antiretroviral treatment, it does actually have a beneficial effect on the underlying tuberculosis, the risk of developing clinical tuberculosis, and the risk of dying from tuberculosis when you actually have it. It's unclear whether this rolling out of antiretrovirals around the world is going to have an effect on TB control. It's probably quite likely it will do, but we don't know for certain yet. Strangely, there is this risk also that if you suddenly re-jumpstart someone's immune system when they have TB, you can sometimes make their clinical symptoms worse because they have this infection. Their immune system's just ignoring it, it's just proliferating in their tissues. Suddenly the immune system kicks in and starts trying to destroy the bacteria, and that can cause inflammation, cause granuloma formation and so forth. And you have this thing called TB, immune reconstitution disease. Another interesting area of development is looking at improved diagnostic assays. So you can get better microscopes that last longer. And interesting, I mean, in my line of work, we're often driven at the very cutting edge of technology and think that the whole world's going to get better because we can sequence genomes and whatever. But sometimes technological advances actually can be quite simple and much more appropriate to situations in developing countries. And one of these was MODS, a microscopic observation drug susceptibility assay. And what they do here is they just grow the sputum in tissue culture medium with or without drugs. They put it in a little plastic bag, so it's sealed off and not an infectious risk. And then they just look at it down the microscope through an inverted microscope and look to see if they can see the Mycobacterium tuberculosis growing. So those cells that are there to start with, if they're cultured appropriately, then they start to grow and divide and divide and divide. Tuberculosis, M. tuberculosis, when you look at it this way, has a particular characteristic appearance known as cording. And using this approach, you can actually detect the growth of the bacterium in about 8 days. And because you're doing in parallel growth with these various antibiotics in the medium, you can actually then very quickly determine whether it's antibiotic resistant or not. A whole range of other tests there, nucleic acid amplification techniques, things like PCR, and this is in fact a big breakthrough. This test here, the SAFED test, expert MTB RIF, and here what you have is you have the sputum goes into a sealed container, sealed cartridge, goes into this instrument, very hands-off. You just put it in the instrument does the rest, and within 1 hour and 45 minutes, it will tell you, first of all, whether you've got tuberculosis in the sample, and secondly, whether it is rifampicin resistant or not. And rifampicin is the most important agent in actually sterilising someone with tuberculosis. And so detecting rifampicin resistant is the most important thing to detect. So this is, if you like, this is a first world solution. This is what we will use in the West before long. And maybe it is being rolled out to kind of middle-income countries as well. Whether it will actually get to the poorest countries is another matter. Another interesting development is the T-spot test, a so-called ELISpot test. What you do here is you take T cells from blood and you grow them out on a medium, and then you can detect, you supply them with TB antigens, and then you can detect to see whether they produce gamma interferon. And this actually has turned out to be quite a breakthrough in terms of the detection of tuberculosis independent of using culture approaches, detection of latent tuberculosis. It actually pioneered in an outbreak in Leicester a few years ago, where a number of people at a higher education college were exposed to tuberculosis, and using this test you could actually see which ones of them had actually been infected and which ones hadn't, which ones were making an immune response. And so this is an interesting new test. I'm starting to run out of time. I'm surprised I've got so much to cover, I suppose. I might even get through leprosy at this rate. Have you got something else after this? So I better talk very quickly then. So let's go quickly then. So multi-drug resistant TB is resistant to rifampicin and isoniazid. XDR-TB is what we call extreme drug resistance. This is rifampicin resistance, isoniazid resistance, fluoroquinolones, and other agents. And we've actually seen a near doubling of MDR cases in the world since 2000, and we are seeing XDR-TB as well. Fortunately, XDR-TB is still much a minority, only about 6% of the MDR-TB, but it's a very worrying trend. There are regimens that work. We still don't quite have a situation where tuberculosis has become untreatable. I mean, there are a few case studies where, case reports where that is the case, but most of the time we still have some treatment options, but the treatment outcomes are poor. And there was this particular outbreak in Tugela Ferry in South Africa in 2006. 52 out of 53 patients infected with this XDR-TB died. And it was only a fortnight from diagnosis to death. So, in a sense, this was comparable to lung cancer again, to a very aggressive cancer. This was a very horrible disease. Fortunately, there are new therapeutic options on the horizon. 5 or 10 years ago, you'd have asked experts in the field, they'd have been very gloomy about the prospects for new treatments. But in fact, there are now a number of them which are in the pipeline and going through phase 1 trials, phase 2 trials, phase 3 trials. And there is a chance that we might actually be able to get even shorter regimens. This particular one here, TMC207, in the right combination actually can cure mice in 2 months. There are also moves ahead to improve vaccination strategies. They're all still experimental. So when we're talking about TB, are we winning? Well, if we look at the global target, we've got this global target success rate of 85% or more for new smear-positive cases. That was actually reached in 2007 globally, but not in 9 high-burden countries. 2008, we got dots in 180 countries, including all of the 22 countries that have the highest burden of tuberculosis. So, 36 million patients were cured between 1995 and 2008, and the case fatality rate dropped from 8% to 4%. And so this is 6 million deaths were averted by using dots rather than previous regimens. So we are making progress here. Case detection rate increased 6-fold, but it's now stabilised at about 60%. So about 60% of cases of tuberculosis are being detected and treated. Target of 70% has been reached only in 6 countries and not yet reached globally. And then we've got 360,000 HIV/TB patients identified in 2008, about a quarter of the estimated total in the world. But sadly, only a small proportion, less than a third of those, have actually been enrolled on antiretroviral treatment. So we still have a long way to go there. This target, though, of actually halting the increase in TB incidence by 2015, it does appear to have been reached already, probably reached it globally in 2004. So in a sense, we've stabilised things. Things are not getting worse. We've actually turned the tide. But currently, we're not actually making much more progress than that. Target a decline of 1% a year or less. In fact, though, it does appear that we're on target compared to the 1990 rates by 20 2015, we will have halved the prevalence and death rates in most regions. We might not quite have done it for the whole world. We still have this threat, though, looming of XDR-TB. There is this risk that if that spreads more widely, we'll go back to days of sanatoria and surgery. So, will we win against tuberculosis? Well, this long-term elimination target of trying to get it down below 1 case per million by 2050, it's not really credible with current technologies and approaches. I think it's unlikely I'll be alive in 2050. It's possible, I suppose. I don't really anticipate tuberculosis being eliminated in my lifetime. It's possible in your lifetimes, it may be. You've got another 30 years on me. Or in your children's lifetime. If you're interested to help on this, we do actually have a very active tuberculosis research program here in Birmingham. If you want to do a PhD in this kind of area, then contact my colleague Del Bezra, who leads the team there. Now, given that I haven't quite paced this right, I was going to tell you about leprosy, but I don't think there's time. So you can read the handout about leprosy, I think is probably the easiest thing.